Okay, well, first of all, good afternoon to everyone. I'm Leonor de la Cueva from the Full Map Project, and on behalf of the entire consortium, it is my pleasure to welcome you to the Battery Ecosystem Summit, fostering cross-project collaboration. Well, we are really happy to host this first full map clustering event here within the framework of the Sustainable Places 2025 conference. So a huge thank to the organizers for providing this platform. And also I would like to thank and make a special thanks to the visionary Battery 2030 Plus initiative for its work in bringing together all the projects in the battery sector. Without that kind of connection, it would have been very difficult to achieve the level of participation that we have today. So thank you for them. The aim of this workshop is to establish collaborative relationship and identify synergies between the 11 projects that are participating, that these are Fullmap, Ultrabat, Safe Loop, Sageli, Batwin, Salamander, Inerrant, Phoenix, Reuse, Batmass, and Open Charge. So thank you to all for participating. And well, as most of you know, the workshop is structured around three different sessions. The first one focus on platform interfaces and predictive design. Then we will go to a smart functionality, safety, and sustainable chemistry session. And lastly, we will focus on manufacturing digitalization and circularity. Each session will feature a small group of short project presentation, 10 minutes of presentation, followed by a dedicated 20 minutes roundtable discussion, focus on exploring synergies and open exchange. Well, uh, this is the short introduction that I would like to do. And I think that we can start with the first session, this platform interfaces and predictive design. This session groups the fundamental work of materials acceleration platform of FullMap, the ultra-fast characterization of UltraBAT, and the interface modeling of OpenCharge. The focus is on the advanced tools and fundamental understanding needed from predictive materials development. And well, the first speaker will be Dr. Mesfin Helmem. He is full-time professor at the Bridge University Brussels and coordinator of the FULMAP project. So Mesfin, if you want, you can start with your presentation.
Thank you, Leonard. I'm going to share my screen. Screen. Hopefully now you should be able to see my screen. Is that okay? Can you be able to see my screen?
Yes, it's okay.
Okay, perfect. Thank you very much. And I would like to start by begin by expressing our sincere gratitude to all the project, the 11 projects that are willing to participate in this Foster Crossing Project Collaboration Workshop. And shortly, I will try to give you, let's say, the general overview of what's a full map project is. And some of you already know what a full map is, but others not. So I'll give you more general overview. So full map stands for fully integrated, automated, and chemistry agnostic material acceleration platform for sustainable battery of the future. That's in short is full map. Our initial point is obviously we all agree that transition towards to sustainability is not anymore an option, it's a must. Then if we want to really achieve this ambitious goal, battery obviously plays an important role. In that regard, lithium-ion battery plays a very crucial role. And it has been already shown a lot of progress as well. But unfortunately, this conventional state-of-the-art lithium-ion battery already reaches to its theoretical limit. And on top of this, obviously, there is also the cost of this material or a battery system quite often comes from the raw material. More specifically, 60 to 70% of its cost is coming from the cathode, the anode, and the electrolytes, which allow us only 30% of playground, which is quite minimal. And on top of this, we have seen that in the last few years, there is a skyrocket demand that's also complicated with this geopolitical factor. Obviously, this means that the price only increase in a year to come. And of course, this means is that we have to find an alternative ultra high performance battery, but not only ultra high performance. Obviously, it should be lower cost and sustainable very urgently. And that's really quite important point we are going to address in this project or entirely in Battery 2030. And obviously, and the question is how we do that. And if we follow the traditional approach, either we need to be magician, which means basically we are lucky enough to bring a solution in a sudden way, or we should follow the trial and error approach, which is the conventional approach where everyone is using, including us in our day-to-day research activity, and which actually cost us a lot of money as well as time. And this has been already evident from many discovery that transfer from research to industrial application, which took really much longer than we anticipated. For example, lithium-ion battery from invention to commercialization, it took more than 2 decades, meaning is that to see the next discovery, we have to wait another maybe 2 to 3 decades, which we cannot really afford. In that case, if that's the case, so we have to really reinvent the way how we really invent this lithium-ion battery. But the other complexity is that research development, as well as bringing, let's say, invention to a market in the field of battery, took a number of sequential steps that also delays the process. And if you want really, let's say, have a solution with a very short time, then this approach needs to be reinvented again. And that's really the main objective or the main ambitions of most of our Battery 2030 project. In this regard, in the format, the ambition is obviously to realize this, let's say, accelerated discovery by using AI accelerated map. That actually will give us the opportunity to define what's really the limit possible entirely. And this can be done by accelerating each and every sequential steps using AI accelerated map. And by the end of the day, we can reduce, let's say, the time that required to bring from research to commercialization. In this regard, specifically, the general goal of FullMap is to develop a fully automated chemistry neutral material accelerator platform for battery material, in this case specifically, and interface. And the ultimate goal is actually to invent this ultra high performance battery within, let's say, 4 to 5 years, which means a factor of 4 to 5 if we compare with the state-of-the-art battery. Eventually, this platform, this material acceleration platform, should be generic enough and versatile, and this will be tested by different use cases in order to make sure the transferability and the usefulness of this platform in general. When it comes to, let's say, how to realize this, and this brings us to the overall approach. As a full map, we will develop, let's say, a broad spectrum of innovative solution in the field of AI orchestration, machine learning, computational design, modular autonomous synthesis, robotics, advanced characterization that towards to develop versatile, modular, fully integrated, autonomous, and chemistry neutral material acceleration platform. And this actually integrates also the interpolability of data infrastructure, which is really the core part of a full map project is. And this we start really by taking also what has been done from the previous project called Big Map. In this regard, just to show you, for example, in our process, to give a very simple example, we can accelerate this battery electrode formulation in a way by automatizing and robotizing the process of the formulation itself. This picture, the one that you see in the left bottom. This is from one of our partner at CPI UK, and the formulation can be connected by a robot, and it can be automated, connected with the AI. So at every process, everything is done by the robot, and the data will be feed it to our AI orchestrator, and the AI orchestrator will be trained and will give, let's say, the next steps of the experiment to be in a better performance. And for example, just to show you a small movie, this is how it's done in reality. So you have your robot and all the ingredient, and the robot is making this sample in a very fast and efficient way with minimum error. And just to give you a perspective, in this case, with manpower, you can produce, let's say, one or two sample within let's say 2-3 days, but in this case per day you can produce more than 241 samples or formulated electrode at different configuration. So this is really fantastic. Then this will allow us to accelerate the process in a much phase. By the end of the day, the idea is the AI will learn how to synthesize this, or how to formulate this electrode, and eventually it will come up with a solution saying that, okay, this is the performance of a certain combinations of our ingredient, and then that will be send a message to the robot, and the robot is going to synthesize it. On the other hand, we recently saw that from publication, by integrating, let's say, this automation process with automated simulation approach, we can be able to come up with the best solid state electrolyte. For example, out of 32 million, we can have this 18 candidate that's really superior than the one that we know in general. So that's the second thing we are also trying to address in this project. On the other point, of course, in this case, we try to really combine AI and the AI precision and let's say speed, combined with let's say the insights of human. So the idea is to use the best of the two worlds. It's not really to replace human by robot in this project. So the ultimate goal is really to solve this critical challenge with the best approach. Of course, in order to achieve this ambitious stuff, you have to have a lot of infrastructure and a lot of people, a lot of expertise and interdisciplinary expertise, obviously. And then in this full map project, which was started in the last February, which was funded by the European Commission, close to 20 million euro. We have a partners of 33, which is composed of big universities and high equipped infrastructure research institutes and industries at different level in this value chains of battery manufacturing in general. And the picture that you see was in the kickoff meeting. With that, I would like to thank you for your attention.
Okay, thank you, Mesfin. I think that we can move to the next talk, and then in the roundtable discuss if anyone has any question or how to bring some synergies with the format project. Okay. The next speaker is Dr. Ivano Ligio Castelli. He is professor at the Technical University of Denmark and coordinator of the UltraBATT project. Please, Ivano, if you would like to go ahead with your presentation. Ivano, you are mute.
Now you should be able to see both my screen and hear me, right?
Okay. One
Can you hear me?
second, because I can hear you, but now I can see the
Okay.
presentation also.
Great. So thank you for inviting me here. My name is Ivano Castelli. I'm a professor at DTU Energy. I'm not actually the coordinator of the UltraBATT project, but I'm one of the PIs. And what I'm going to talk to you in the next 10 minutes or so is about the need for understanding better dynamic processing batteries. Because what Mesvin showed before is a great example of how to develop materials aggregation platforms for discovering the next generation of electrodes or electrolytes, but then there is also a need for a better understanding of what is happening in materials themselves, and then use this knowledge to build up new batteries. And the reason why we look at this is because batteries and general interfaces are everywhere, and they also span a very broad time and length scale. So we have effects that they happen at at the femtosecond or picoseconds level and the picometer, so typical electron transfer, but then also at the larger scale where the ions move, so lithium intercalating or alloying to the electrolyte or the cathode, dendrite formation, what is the effect on the composite electrolyte, and so on and so forth. So basically what we want to understand is the smallest part of this problem, and at the atomistic scale, so femtosecond, picoseconds, where each atom matters, how the electron transfer happening from the electrolyte to the electrode, and the same for the ions. And to do that, we need a multi-mode and multi-scale approach where we combine high-level experiments with a theory that is as accurate as possible. And this is what UltraBATT is about. Is a project that started 2 years ago, and we really try to tackle the question: what happens at the interface for ions and electrons? And so let me tell you a bit about the project itself. It's 4 partners plus 2 new associated, 4 members plus 2 associated partners. Is us at DTU. We have 2 in France, Collège de France and CNRS, XFEL in Germany, but then also we have as partners Warwick and from Slovakia, Peter Sifalic. So you can see that here we really span everything from the theory to experiments and vice versa. And we use the expertise of all these people here. So yeah, the basic question is how can we which kind of experiments or which kind of theory we need to do to measure electrodynamics in batteries, and in particular looking at how polarons are coupled with charge trapping or phonon distortion, and how we can drive or control electron transport. And then we can also do the same with ions. What is the charge density or the electron charge that can trap ions, how the ions can move, what is the relation between ion movement and electron movements, so the polarons and ionic trapping. To do this, we do on model systems, and we identify 3 different cases. One is the lithium. They're all very common cathode materials and famous for different reasons. We go for lithium manganese oxide, which is a commercial cathode material, which show a structural change during lithiation. And there's also as an example that is very well studied. So basically what we want to do is using the knowledge that we have, the experimental input and so on and so forth, to better understand something that is already available and used, and then use this knowledge to build the materials of the future, right? And for LMO, it's important that we have a fast exciton dissociation, which we think that leads to polaron formation. I will show you in a little bit how polaron behaves. Again, for vanadium oxide is another important cathode material, very well referenced example, and also shows a phase transition at this point. And then the lithium lanthanum zirconium oxide, solid state electrolyte, good ionic conductivity. The single crystals are available commercially, so it's a material we can actually test in a very accurate way. And everything starts out of the atomistic scale, where we do high-level theory, high-level density functional theory, to understand how the polarons are formed and how the polarons and exciton in general moves in the crystal. And to do that, we use an autonomous workflow managers, which actually allow us to orchestrate all the simulation by themselves, in an automated fashion, where we go from the most common relaxation to actually very advanced simulation, where we calculate how the polarons really are formed and how they move in the system. Then you can actually look at if there is a order disorder or displacive transition, how the polarons change during a different temperature, what kind of charge transfer you have. So you can see here, for example, in some of the Van Vleck mode, when you go from +3 to +4 charge, so where you can assess, okay, the polaron is here or the polaron has been moved somewhere else. And then it's important that we combine this information with also experimental input. For example, we can get structural information from XRD. Again, here we use very pure sample, single crystal samples, very accurate experiments, because we want to correlate very idealized experiments with a theory that is as good as possible, right? And again, we can look at how the basically where are the peaks of the structure information of the material during charge and discharge during different lithiation stages, and then directly correlated with the theory that we are developing. We have been at a few times at beam time, which allow us to really understand these fundamental properties. So here we are shifting from a more explorative project to really understand what is the information of the battery interface that we are missing and developing that. And this is all work that we are doing together. Is involving several people because we are using the expertise of everyone, coming from science dynamics, X-ray, resonant emission, X-FEL measures, and so on and so forth. Yes, of course, this is one of the techniques that we are actually using also that is that we believe it's really powerful is the pump probe. The Raman experiments, but also combined with pump probe techniques where we actually inject electrons in the system and we look at how the system behaves. So going beyond actually just charging discharging, we're actually forcing more electrons into the system, which is a unique technique that we can use in this case and combine it again with different levels of simulation to have a one-to-one map in between the two. Just interested on time, I'm skipping to here where are we and what we want to do. So we are working on two main candidate material, LMO, LZO, and really again try to understand what is the fundamental properties of that. That is something that we feel that is a little bit missing in the community right now. Complementing different techniques from experiments, theory, going to large-scale facilities and so on. We have had two X-FEL beam time slots in this year, so we are actually analyzing the results and combining those results with the theory that we are developing. We have actually used also one of the hop-up projects that the European Commission allows to get Peter from Slovakia involved, which is actually a good way to include more partners or more expertise into the project. Yes, and that's more or less it. And these are the people that are again involved and that have been part of the project so far. Thank you again for having me here.
Great, nice talk. Thank you, Manu. Okay, let's continue with the third speaker.
Yes, hello everyone. Sorry, I'm not the best using this this device. So yes, thanks for the nice presentation. How you see, this is a bit like a general question more, but how you see the future of the batteries and battery business in Europe in the short and long term? I know that the question was a bit out from your presentation, but it is, I think, quite an interesting question to discuss.
Yes, for sure. The question is directed to Mespin or Ivano, or is an open question for the
It's an open question to all of us, I would say.
So that would like someone to answer.
Sorry, my audio went down for a second. Can you please repeat the question?
Yes, I was just asking for the curiosity. So how you personally see the future of the batteries and battery business? Because we have put quite a lot of effort on the development of the battery ecosystem in Europe. So how you see the future of the battery business in Europe and in the short and long term, and maybe also that what would be the most potential initiative we have here in Europe for battery business?
So I think that Battery 2030 Plus was really one of the first initiative that, or probably was the first, that tried to develop a battery ecosystem. And I think for some extent, then was actually able to do it because they managed to get 200 different people or even more sitting down in the same place and discussing about batteries and creating new synergies. I think one of the main limitations that was of the ecosystem at that point is still that we are depending on fundings of the European Commission that is 3 years or 4 years projects, right? So it's all sort of semi-short term where it's very difficult to go from a university scale to actually a commercial scale. So that is one of the things that I could think of it, something we could do better. And in general, I think that we shouldn't think of battery as a one single technique or one single chemistry, but needing really I don't think there would be one battery that makes it all. We'll need to have different technologies and for different uses. And for that, I mean, it's necessary that we better understand what are the fundamental properties, because at the end of the day we are still researchers, and I mean, knowing better how a battery behaves in different conditions.
Yeah, personally, I don't need to have any correct answer to that question, because I think that it is everyone is thinking about what will be the future and how there are so many other issues affecting not only research what we do, but also geopolitical situation and so on very much. But thanks for the answer.
Okay. I know that Mesfin was trying also to comment, but I don't know if he can do it because he cannot unmute himself. I'm asking the organization.
Okay, just to add what already Ivano said, I mean, the European wise, I think we are a bit behind compared to the other partner working in the Far East in terms of, let's say, technology. But I would say in terms of innovation, we are really I believe we have really a solid foundation. That's really quite important for the future. And if we keep really going this, let's say, joint effort within the umbrella of Battery 2030, I believe in the coming 3-4 years, and then we can really be in the upfront of this, let's say, battery innovation framework. And then for us, I think as Europe, this is not really the option anymore. It's a must. And if we really want to realize this transition to sustainability, this is the only way out for us. So it's not really the option we choose, but it's a must. We can go to that direction. So as a researcher, of course, we have to contribute our roles. But of course, by the end of the day, this should come to the society, and we should be able to see it also the impact. So working with the companies, those can bring the impact immediately is very important. And as a full map, we try to do that as well. I think Ivano also did the same in the field in the previous project in Big Map, which bring a lot of companies together to see, let's say, the short-term impact into the community as well as to the European battery ecosystem in general. And I'm quite hopeful we will continue in that way, and hopefully in the coming 5 years there will be a lot of change. Obviously funding will be a big constraint for sure, no question at all, and the chance of let's say getting this project granted is not really easy anymore in the near future, but that's one challenge. But I'm quite optimistic we can play a very important role in the near future as well.
Thank you, it's Mesfin. Yeah, are there Someone that has any question? Okay.
Can I add one thing?
Yes, of course.
Maybe another important thing is now compares to what we have been 5 years ago. 5 years ago, everyone can go individually. Each group can do research separately, and of course can make a kind of impact. But now to really bridge this gap we have with our competitors, working together or joining force is a must. And that's, I think, one of the idea of this clustering event organized by the full map. So there is really a lot of complementarity between different projects and different research partners from all over Europe and industries. So the best way to really overcome the challenge are working together. Networking and collaboration is really quite essential. Thank you.
Yes, for sure. I think that that is really needed. Okay, we have a question in the chat from Esha Kanwal. How can we integrate gentle or distortion insights from computational models into the sustainable design of a stable cathode electrolyte interfaces, especially focused systems like lithium manganese oxide or vanadium oxide, where lattice dynamics strongly affect cycling durability?
That's a very, very good question, and I think we are at the point where we cannot we don't know yet how to include it, in the sense that we know so little about what are the effects that control the dynamics of excitons and polarons and so on and so forth, that we need to understand this better before being able to proactively use it for something good. So I think that that's where actually the UltraBATT project focuses on a very, very low TRL, because what we want to do is understanding the properties first.
Okay, thanks. Does anyone want to address any question? So, for me, concerning these projects and how we can collaborate, it's important to know how we can extrapolate results from one project to another. For example, we would like to have a chemical agnostic platform, so with models that can predict behavior and and different parameters of the batteries, since how it's going to degrade the cathode, or well, even problems during conductivity in the electrolyte, etc. So for me, having here Ultrabat that you are really focused on applying new techniques, new characterization techniques, um, to different materials, how we could take advantage of this information and this new knowledge, and how we can consider that since the beginning, for example, in our work to predict to predict and try to design new batteries, having this new information.
Should I take it?
Well, yes.
So I think I mean, you are actually asking something very interesting and is very challenging. How do I make sure that my models are usable for somebody else? And that is not trivial, in the sense that we need to be able to develop a platform that is not only delocalized or decentralized, but also synchronous. And you can say, who pays then for this? Because at the end of the day, I mean, you have several researchers that work on it, and the infrastructure in general is run by somebody else. Uh, I think that for now, I mean, the projects like Big Map or Full Map are the ones that show first how to you can develop a map for a project specific for a project, but this is clearly not enough. We need to be able to make a map of maps, so a place where you have a lab that are at the service of other people, similar to what synchrotron or large scale facilities are. When I have an expertise, I mean, my group is doing modeling, so we are expert in that. We always try to make our models interoperable with what is already available in the community. So then you can publish them. It's much harder if you think about experiments, but in German we need to think in a way of not only how I can use my equipment to make a specific experiments, but also how can I make my equipment general that can be used by somebody else.
Okay.
Just to add
Please,
one more
Masmin.
thing is, of course, on top of what Ivano already said, mapping is very, very important. And on the other hand, if I take, for example, ultrabats, they are really focusing on interface designing or interface understanding. And that kind of insight is really quite very, very important for, let's say, designing new materials or new systems in general, because by the end of the day, even though you end up discovering, let's say, the best solid state electrolyte or the best cathode, if you don't have really nice interface or stable interface, then you end up having poor battery actually. So interface is really quite critical. And then maybe one of the collaboration way is exchanging information and exchanging of data could help us, let's say, to from the beginning on to start really including this kind of concept or ideas or data into this map, and that will guide us to come up with something more generic that includes also interface problem. That could be one of the, let's say, the starting point where we can collaborate between the two projects. Of course, in the full map, we have interface designing work package, but of course, joining force in that aspect as well, it gives a benefit for both of us, I believe.
Yes, Ivano?
Yeah, so this is something that we actually started in the Big Map project, where we had a Big Map infrastructure, which was used by, I mean, at least a good fraction of the Battery 2030 plus people had an account there. I can see one of you in the room here actually contacted me some time ago to actually get accounts for their project, and will reply soon. So I think I fully agree that that there should be a data is a key to cooperate. I think that there is still the problem of standardizing data, because data themselves, they are not, I mean, curating data and standardized data and metadata, because the way that I save my data is different from what you guys do. So it requires a bigger effort and consensus from the community. But it's something that, again, with some of the I think it's Work Package 3 of Battery 2030 Plus, we are actually doing. But then again, it goes back also to the question of how to deal with long-term storage, and how to in general to make data and metadata interoperable with each other. That is not super trivial. So I think that the data is really the way to go, but it's not something that can be it's super easy.
Okay. Well, I think that we can start from that and continue the conversations and try to see how we can benefit to each other and try to explore this connection and how to do. I don't know, but in a way that we can take advantage of the results since the beginning, or at least in this case, the full map project. So I have one question for Ivana, but maybe this is because of my misunderstanding. That you were talking about exfil measurements. So I think that I think that this is like a synchrotron measurements. Am I right? Or
Yeah, so we
and
go. I mean, I don't, but we have partners going. Yes.
okay. And which are the advantage of that kind of infrastructure?
I think is reaching sizes that are not achievable on other experiments. So
Okay.
both in time and landscape. So where we actually can pinpoint when the exciton is moving or what is the structure of the of specific structure.
Okay, thanks.
And then
I'm
of
not
course
so
there's an
familiar.
issue of I mean is a you get funded, but then you also need to apply for beam time and go there. So it's actually a slow process, but it's a fundamental knowledge that we need to develop in order to to know better how a battery works.
Okay, thank you. I'm not so familiarized with that kind of infrastructure, so that I could will thanks for the answer. So I don't know if someone has more questions or would like to comment something more for in this round table. How to connect, if there are other projects that can support this work. Yes, Samson.
Yeah, I just wanted to say some feedback. I think one of the things that really kicked our effort into getting involved with data handling and thinking about standards and all this stuff was this data workshop that was in January of, I think, maybe 2 years ago or a year and a half ago at Big Hub. But I think it really helped bring like a lot of awareness to this and challenge the projects to actually make it a priority, which I think is what we need to motivate in each of the projects, because of course we have lots of things and that we are juggling, but it takes a bit of a repeated exposure to this idea, and then getting some people to really champion it or be responsible for it in each of the projects, and kind of like a data handling person. And I did that a lot for Salamander, but it was very hard for me as coordinator, but I eventually got someone else to help with me with that, and I think that sort of we've made a lot more progress because of that, but it definitely was kickstarted because of this kind of workshop. So I really encourage like Full Map to do something similar to kind of carry on the momentum, because I think that's it was really helpful, I think, to have that workshop.
Thank you for the suggestion. Yes, I think that we can do some effort on that regard, and make more and spread the word about what we are doing and how we are doing, and how researchers can work with us collaboratively in order to feed our platform or databases, and have more information there. Thank you, Samson. Yeah. Okay, Ivan.
Yeah, and I just want to say thank you to Samson because I was one of the organizers of that workshop, and I think that I mean, of course, I did it, so of course I think that it was great. But is really what you say is really important, and the fact that the material science community here is a decade behind natural bio. The field of biology, right? Because they are much better at storing data and sharing data compared to what we are. You can say maybe it's because our data are not so long time or challenging or expensive to make, but clearly we can also learn from other communities, and that's what we did 2 years ago, a year and a half ago, in the workshop. We tried to bridge the not only batteries, but we had people also in catalysis. We had journals. I mean, we had invited one of the editors of battery and supercaps, because what we needed was also being backed up by actually the journals themselves. I mean, we need to establish a culture not only of publishing papers, but publishing data and publishing codes, so publishing
Mhm.
standard presenting procedures, because otherwise, I mean, it's the way that we push forward the community, and that's a problem with if you think of, I mean, our career was based on papers, but the next generation of researchers is not given that is based on papers. It might be based on data. In some cases, your data set gets downloaded and published more than actually, and the user cited more as a data set than the paper itself. I can tell you that I was at the PhD defense a couple of days ago, and one of my data set from more than 10 years ago, 12 or 13 years ago, was used as a benchmark. And then it's like, I mean, how much it gets cited the paper that is 10 years old, but then the data set might still be useful if you store them right with the right data, metadata, and so on. So we need to change the mindset of us and also of the students that the data set is as important as publishing the paper, and the data set should actually be together with the paper, not as two separate entities. But thank you for the nice word, Samson. I think it was great to have you there, and yeah.
Yeah, so I'm looking forward to the next thing to kick off that, more activity in there.
So we can make some joint activities on that in that respect. I don't know if Ivan or you continue doing this kind of workshops. If not, well, we can try to move forward that kind of activities. Yes.
So that workshop was actually part of Big Map and part
Big
of
Map, yeah.
Battery 2030 Plus, because we felt that there was a need of putting together different communities. I mean, as I said, it was battery and electrochemistry or electrocatalysis. Within Battery 2030 Plus, there is a full work package dedicated on data. We are developing a MOOC on data and metadata storage together with people at Sintef, Simon Clark. We have actually advertised or shown example at the annual conference, I think was in May. We are preparing the paper now, and that will be fully available online and free. And we believe that that is the way that we can sort of start with having students in a sort of in a MOOC way to share these things. Of course, data is not. It's very difficult to get fundings for data, right? So it has to be a larger infrastructure that allows that. There have been a course and initiative that probably will come up where data are the key. I mean, there was if you have seen Materials Common, for example, is one of these cases that really leverage on data across multi-scale, multi-fidelity, multi-source, right? But clearly, I think we need to start bottom up and having the students understanding the power that there is in data also for their career, and not just for our own sake to have the data that is backing up a paper.
Okay, thank you for that information. That night we will coordinate also with Battery 2030 Plus and regular meetings. Thank you.
You're welcome.
Okay, so the time for the round table is gone, but hello again, everybody. Now we will start with the session 2 about safety, smart functionalities, and advanced chemistries. This session combines projects focused on safety and sustainable chemistries, like could be safe loops, agile, inerrant, with those implementing smart sensor and healing functionalities like Salamander or Phoenix. The goal here is to creating safer, smarter, and more resilient next generation batteries. So the first speaker is Dr. Ulayasi, professor at and head of the research unit of sustainable chemistry at the University of Oulu, and coordinator of the Safe Loop project. So maybe Ulay, you would like to share your screen and start your presentation.
Yes, thank you. Can you see my screen now?
1 second.
Is this just wait a second, is this just now I will see it, but I will try to show it to you. So let's try. Can you see it now?
Not yet. So
Ah.
you have to click on share screen.
Yeah, exactly. Sorry.
And then
And now you can see. Sorry for this.
perfectly.
Yeah. Okay, so good afternoon, everyone. Here from Finland, I'm Ulla Lassi, as introduced, and I'm the coordinator for SafeLoop. SafeLoop is the one of the Horizon Europe project with the aim to first to make full cell batteries for EVs. Actually, our application is a bus, which is the end application, and we are securing this kind of like a secondary material use without compromising the battery safety in our work.
Ulla,
Yes.
excuse me. Can you maybe when you present the slide, don't use this mode, but use the.
Oh, okay,
Yeah.
okay. Sorry.
No problem.
Is it now better?
You have to reshare your screen, please, on the Ring Central.
This one?
The Ring Central stopped streaming your screen, so you should come back on the app and click share screen.
Okay, I will
Yeah,
try to
please.
do it again. Sorry for
Sorry.
that.
No,
No problem. I will try to
Okay.
see what you see. No, you are not seeing correctly yet.
Click the slideshow and then.
Yeah.
Yeah, no, that's a presentation view, presentator view. So come back.
Can you see it now correctly?
No, we see the presentators.
Oh, what is
so
that?
that's not
Because
the
it
right
works. Sorry.
No, sorry.
Wait a second. I will try to fix the problem because it works when we test it.
Yes, we tested like earlier.
And
So
can
when
you
you go
screen now, Sarah, because I see it as a full screen.
Yeah, but we don't on our side. We see it on as the presentator. So. Like we see an interface still. So when you're on here, you click slideshow and then play from start. Okay.
Is it now correct?
This is not correct, no.
Yeah, but for my screen, it looks to be correct. I will try to once again speak it. Is it now correct?
Now that's perfect.
Okay, good. So to continue, so we have 15 partners, of course, mostly in Europe. Oulu University is the coordinator partner, but we will then have also associated partner from United States and also from Australia. And then one from the United Kingdom who is not yet a partner. So basically, we are quite well and fully covered the whole Europe. And actually, I would like to highlight that we have also 2 Ukrainian partners in the project, which has been, of course, a nice pleasure for us. If we then look at the SafeLoop aims, what we aim is, of course, to secure the safety for the battery cells, whatever we are doing, and improve the sustainability of our cells. So we are aiming to use the minimum recycled content of the recycled element in our battery cells. And starting, of course, from the laboratory scale, we will go then to a really big scale where we are talking about then already in like 10 ampere hour battery cell capacity. All the cells will, of course, be tested also for the safety. We'll have one partner taking responsible of that. And of course, all the cells will be then tested for the performance. So we aim that as a final target that we will increase 15% of cyclability of those battery cells by doing doping and coating of the cells, and at the same time also that we will really reach those very ambitious targets of the EU new legislation related to material recovery and the use of the recycled content in the batteries. And last but not least, we are not focusing battery safety. Here is an overall flow sheet of our project. So basically all the key battery components, anode, cathode, separator and the electrolyte are in our focus. Most of the effort, of course, we are putting from the recycling viewpoint, the anode and cathode side. We also, by the Ukrainian company, we also focus on the coating of the separator. And then also to develop an electrolyte which is then matching and is compatible with the whole battery system. Anode materials are mostly made on recycled carbon materials, carbon precursors. This kind of like not only recycled graphite, but also different carbon residues, which are used as a conductive agent materials in our electrode materials. Cathode chemistry is NMC 88. And in order to, once again, to fulfill the criteria of the recycled content, will we use recycled elements from batteries, spent batteries, and also this kind of like a thin alumina coating layer, and this alumina is also recycled element. So we will then focus on the, after testing and making all the key components, we will then focus on the assembling of the pouch cell by TÜBİTAK at Turkey. And for those all cells, we will then carry out battery safety testing according to standard procedure in Poland. And then at the end, with the best and the optimized chemistry, we will then focus on the production of bigger battery cell packages, and the end testing is done in collaboration with Pochankaya, with the focusing of that battery management system and battery package to be tested in the e-bus conditions. There is, of course, a lot of work and coordination with the material flows, because we are, as you see, the whole global planet is covered from United States, Europe and Australia. And that has been also, to be honest, a challenge for the project. So material flows, and especially the lack of this kind of like a recycled material content, which was a little bit surprise also during the project. Then we have also a lot of communication activities and activities related to LCA and circularity evaluation and IPR issues in the project. Shortly speaking, one big work package in our project is related to innovative approaches in the new anode active material. Not only making the new anode active material, but also to improve the performance enhancement of these anode materials. We mostly work with the silicon and different conductives from the silicon, like recycled graphite from spent battery cells, but there is a small, more in the research level activities in the silicon powders as well. In the project level, we are talking about in the final stage, we are talking about that we will then use something like a tens of kilograms of active anode material for our battery cells. Personally, I do know most at the best the VP3, where we develop the cathode active materials for EVs, and this is based on the use of a recycled content in material flows. And then in the laboratory scale, using quite a big reactor scale, something like a few liters, I would say 5 to 6 liters in the reactor scale, we will then co-precipitate those precursors for batteries and then lithiate them to get the nice or less nice spherical particles. Our focus in the project is in NMC 88 chemistry, but then we use also other chemistries, mostly NMC 811 as a reference material. And also here we use not only recycled elements, but also then conductive carbon additives, which are also materials from the recycling. Then our Ukrainian partner, UNESCO, will work with the battery separators. They are developing battery separators which are coated on a thin layer of the nanoscale alumina with a very small content of the nanoscale alumina to improve the battery safety, especially when we use the high C rates for battery testing. One part which is done in Germany is focused on the electrolyte development. So when we have like a cathode, anode, and the separator concept available, then we will optimize our electrolyte system. Once again, it plays a key role for the battery safety to be non-flammable electrolyte, and then it will be then tested and improve the electrolyte stability with the long cycling test before then this electrolyte will be introduced at the final stage to the battery cells. And then VP6 has been maybe the most demanding of our work because it contains everything which is related then to assembling of the battery cells first and then battery packages of different size. And it also contains battery safety tests. So the battery cells in a small scale will be tested first according to standards so that we can confirm that all those, for example, impurities which are introduced from the recycled material contents are not affecting on the battery safety. And that is done in Poland, in Poznań. Then there are also work related to sustainability. So we have an Imperial College of Science Technology in United Kingdom who is taking response on not only on that environmental impact, but also looks the risk assessment together with the other partners, and then we also evaluate the techno-economic feasibility. So building up one of the first this kind of recycled battery cells for the real application, it's very important to look at all the aspects of the work. Even we have this kind of like also very fundamental research viewpoint here, but we like to confirm everything before then testing our battery packets in e-bus. And then last but not least, and also a part of my work today is our communication and dissemination. We have promised that we will produce 15 scientific publications and deliver also a lot of other active communication and dissemination, and that is then coordinated by NVIVA. We are also an active partner in BATT4EU Europe and Batteries European Partnership, and also in this Battery 2030 clustering network like today. Now the project has going totally, we are not in the half yet, so we have something like 14 months behind, so we are quite in a good progress, but as a coordinator I can also say that it has been very, very challenging to be a coordinator for this kind of project where we go through the whole battery value chain, because no one of us, of course, has a competence in all. But that was shortly what we have done, and if you like to contact us, we have a nice web pages thanks to partners, and also we are quite active in the social media, so you can find an updates from our project. And I would like to thank key persons behind the Safe Loop for good work they have done for this project. Thank you all.
Thank you very much. Thank you for your presentation. So let's continue with the talks, and then in the roundtable we can discuss about the different projects. So next speaker is Dr. Colin Jean-Francois, a researcher at SEA Litten and representative of the Sageli project. Okay.
It should come. Yep.
Now, perfect. Yeah.
Yeah. Good afternoon, everyone. Sorry. So yeah, going to present you the SageV project. So SageV project is a sister project of Inherent and SageLoop. But we started a bit later than them. We started at the beginning of the year. So it's also a project that will last 3 years. We are 13 partners with 5 countries. I will go a bit more into the details. And we focus on this concept. We keep a quite simple liquid electrolyte concept and decided to work on 3 different components, which are the cathode material, the cathode material, which is in most of the cases the one that is starting the thermal runaway at the big in the cells, the electrolyte, which is giving fuel to the thermal runaway, and also the binder, which is a component that is often overlooked in project. So in terms of cathode, we are running away from the cobalt metal and also from the nickel. We will develop 2 generations of material with high lithium content, but also high manganese content, as manganese is often believed to stabilize the thermal behavior of material. So, and we will go from 20% of nickel in the layered oxide to 0% of nickel in the disordered rock salt. And the idea is to both improve the safety, but also not sacrifice seeing the performances. This material at the end, they should be able to perform better than the LFP. So this is a starting point. So we have already good performances during the first cycles. We have a lot of work to do to stabilize the second generation material, but at least we know that this material, they can perform well. And our strategy to stabilize this material is to work on both their morphology and their surface. We know that solid rock salt, they have a quite diverse morphology, as you can see, and the idea is to go closer to classical spherical agglomeration from the cathode material. The idea is to be able to have a much better coating on that if you have a more regular surface, and then the coating will be done by ALD to assure a conformal coating and better stability of the interface between the cathode and the electrolyte. So the idea is to reduce by a factor of 3 the gassing of the material at high potential compared to the NMC 811, so to remove a part of the fuel of the thermal runaway. So of course we have done a baseline for the NMC 811. That is one of the first result of the project, as we start quite just this year. So we know what we have to reach now with our materials, but of course we will need to build more representative cell with our material before doing this kind of test. We also work on binders. As I said, that's something that is often overlooked. The idea is to increase the binder adhesion coefficient and to increase also the stability of the slurry. The adhesion is important in terms of safety, because if you have bad adhesion, you can have then higher resistances, and then that's where you have overcharge on part of the cathode. And the stability of the slurry is very important for the handling and the processing of the electrode, so that you can produce electrode with good performances and good stability on a longer term. And of course, we are also working on electrolytes. As we go higher in potential than the classical NMC, we have to find better electrolyte at high potential with good ionic conductivity, and we will bring in better non-flammable additives to increase the safety of the electrolytes. Everything is done through a high throughput experiment design at Jülich. So with that, we target we are targeting cells with different dimension depending on the generation of material. We are targeting quite big pouch cells for 5 ampere hours for the HLM, which is the more mature material. That's already a challenge because we will have to scale up the production of ALD to up above 1 kilogram scale. Have to optimize the formulation too. And for the dearest material, then it will be a 25 milliampere pouch cell, so it seems low, but at the moment there is no full cell known for this material, so that will be the first time we will demonstrate full cells for these materials, and we'll be able to test the safety of this material. I'm sorry, I lost the app. Okay. And of course, there will be safety tests. So classical thermal tests, overcharge and nail penetration. What is a bit different, we will do it at different SOH. The KPI is here is you have to reach a UCAR level of 3 because we are targeting maritime and aeronautics applications, where the safety is even more important than for cars. And to help the safety prediction, we also developed tools for assessing the safety of the materials already at small scales. Usually the safety tests, they are done at big scales where you have already mature cells. The idea is to be able to help the material design by having prediction tools at the material scale, so having thermal runaway tests on small amount of materials with the equivalent of coin cells. And this will be also supported by development of state of safety model that will combine both safety and aging parameters to have really the idea of a state of safety at all the different step of life of a cell. And for that, we have the consortium expertise of the different partners. So as I said, we work on the cathode, so it will be a work of CNRS, CA, and Umicore. Binder research is done by Arkema. Electrolyte is carried by Jülich. All the safety by design and the cell making will be done by CDTech, CN Energy Gune, and CDCells. And we also have, of course, LCA and analysis by Lomatov. And we have different end users from maritime and aviation, so Fincantieri and Safran, to help us knowing if we are going in the good direction. So with that, I would like to thank you for your attention and thank the consortium for their work.
Thank you very much, Jean-Francois. Colin. Let's move to the next speaker. Is Dr. Spiro Giannopoulos, but I think that he is not connected, or at least I cannot see him in the list of people that is connected. So, Spiros, are you there? I think that no. Okay. So, well, maybe Samson is not a problem for you. We continue with your talk. Samson, Dr. Samson Yushulai is senior scientist and group leader for materials development at the Institute for Energy Technology and one of the coordinator of the Salamander project. Yep.
Yes, hello. You can hear me? Yes, great.
Yes, perfectly.
Okay. Yes, my name is Samson Lai. I'm the coordinator for Salamander, and I'm just going to talk about recent progress in our project regarding self-healing functionalities in lithium-ion batteries. So Salamander is a smart functionality project, but I don't really have time to go through the entire aspect. So I've just kind of primarily focused on sort of our recent results in self-healing. But this is the overall approach. We have self-healing on the anode side, so we're using a silicon carbon composite electrode system. And so we have two different self-healing polymers that we plan to integrate. One to work on the silicon nanoparticles themselves and focus on protecting them and keeping them together as a microcluster and avoiding some of their separation from there. And then we have another self-healing polymer that's kind of throughout the entire anode, and that's for helping through the overall properties of that electrode. On the cathode side, our approach to self-healing is focused on these kind of scavenger capsules or microvesicles. These are carrying some sort of active species or sacrificial lithium salt, and it's targeted towards some degradation mechanism on NMC cathode. So in addition to this, you would also have sensors. As you can see, some of the sensors were printed on there, and these are all connected through a BMS. Like I said, I won't have time to talk about all of those, but I think it's more interesting to talk a little bit about sort of our results and progress on the self-healing aspects. So for the self-healing anode, as I said, we have two different polymers. One is this covalent adaptive network. This is a type of polymer that has very nice elastomeric properties. You can make films of it, and it's kind of stretchy and things like this. In the figure in the middle, you can see that there's a cut that's made, and actually a macro scale cut. So this is optical microscopy, nothing very high resolution. But with some application of modest temperature and time, you can actually see this cut heal itself. And so the idea is this is how the polymer can heal different cracks or different damage to it. And it can also be derived from bio-based materials. So we have that circularity built in. So our family is called curable polyurethane ureas with hindered urea bonds. I'll get into that a little bit later. The other type of polymer that we have is the semi-zwitterionic polymers. And these are more like very similar. They have self-healing properties, but these are more less temperature activated, more present throughout the entire anode. So for that first type, covalent adaptive networks, some complicated organic chemistry. You don't have to know all of this, but the main thing is that you make a kind of long chain of this. And the key part, that's the self-healing part, is this kind of hindered urea bonds, where these bonds can actually break apart, and then through the application of heat, they can actually reform, and that's how you get the self-healing functionality. And then the rest of the polymers then you use for tuning the properties of that polymer, so making it the right viscosity, making sure it's a liquid or cross-linking ability, or these kinds of things. You can also tune that self-healing temperature, so that's kind of also where those aspects come in. The other type of polymer that I was talking about, semi-zwitterionic, these are basically made of dual ionic monomers. So it's a single polymer chain, but on that single chain, you have both cationic and ionic moieties. And so that's what creates this semi-zwitterionic properties. But it allows this, then you can have basically ionic interactions between polymer chains, and this allows you to have basically these polymers can then come apart because they're using ionic interactions, but then they can come back together, and that's how you get the self-healing properties. And again, you can tune these polymers based on like chain length and these kinds of things to make them to adjust those types of self-healing properties. So we thought, okay, we have these self-healing polymers. We've already have demonstrated that they can do self-healing quite well. So it's just a matter of just putting them into anodes. And so we thought, let's just put some into the anodes and figure out how we make them. They're very much similar to how we make binders. So let's just use that. We just replace the binder with this, for example, this zwitterionic. And we got some really serious challenges, actually. We had really bad electrochemistry. The first couple cycles really died. And then we had to spend a lot of time figuring out what was going on here. So we applied a different battery of tests. So we thought, maybe it's our silicon. That's our silicon's problem. Let's try a different silicon. So we used a commercial silicon. And we observed the same kind of degradation really fast within 3, 4, 5 cycles. So this is really confusing to us. Let's go back to something more simple. So graphite. Is it just the electrochemistry that's polymers not compatible with? And we actually found a really nice graphite performance, possibly even better than what we normally get with regular binders. But our project isn't focused on graphite so much. So we haven't been able to explore this necessarily because we have to focus on other things. So we thought maybe then it's volume expansion. Silicon has this alloying ability, it creates cracks and volume expansion. So let's test another material, tin, which also has volume expansion, but maybe it's that, and can we isolate that? And we actually got a pretty normal curve of what you would expect for tin in terms of performance. So you get this gradual degradation, and then you kind of get a low spot, and then onward. And so that kind of explains that it wasn't the volume expansion, because this sort of is working there. And then when we do a graphite silicon test, maybe it's just electroconductivity. But in the end, we actually got performance basically proportional to the amount of graphite that we have. So flat, but lower based on that. So we kind of demonstrated through all this testing and a lot of failure, but we were able to see that the electrochemistry is working, but we're not able to really see the self-healing. So we tried to self-heal some of these polymer batteries, and they didn't really show any difference. Of course, sometimes there's no degradation to heal, let's say. But what we basically have found out is something to do with silicon that's really interrupting this process and just doesn't play nice. So we have actually ended up, through all this feedback, developing a new polymeric binder through this iterative design and testing. And so now we have something that's kind of a different approach. So rather than having a self-healing polymer that we know has trouble with electrochemistry, we actually developed something that has good electrochemistry, shows that it can work, but now the self-healing is sort of the part that we need to tune a bit more. We had the same issue, actually, surprisingly, with the covalent adaptive network. So a totally different type of polymers, and still the same issues. So it was really a difficult time for our project to just start. But we did end up designing a sort of a new polymer using a siloxane-based chain, reasoning, thinking that maybe these polymer chains are just too mobile and they're not really attached to the silicon. So we thought, let's add this kind of siloxane functional group and then make it so that it's covalently linked to these particles. And then we also have this self-healing aspect, which can then kind of connect these two particles together. So we were able to do that. We were able to characterize that we made the right polymer. We had some issues now with self-healing, right? So the self-healing isn't working as we intended it to. But the good thing is that we actually did get some decent electrochemistry. So we had a coating, we were testing different loadings of the coating of the silicon particles with this polymer. We're able to get about 2, 3%, 4%. And we're able to actually see some nice, decent electrochemistry. So again, kind of using this reverse approach to what we have. So we still have to see whether we can actually, let's say, heal the damage and do the self-healing, but at least we've finally made some progress after a long struggle in the beginning. On the cathode side, we set this approach with using microcapsules in this platform, carrying these structures. So they either have, for example, manganese scavengers to pick up dissolved manganese ions in the solution, or lithium sacrificial salts. So those can just be activated and sort of increase your lithium inventory. This operates basically a very bio-inspired design from like immune systems or healing, like platelets, and they kind of just float around, and then you can activate them accordingly to release their important, the trigger or the key species inside. So it's relatively straightforward wet chemistry method. We selected porous silica shells as our kind of platform, so we can create those from wet chemistry. And then we also chose this lithium squarate as our sacrificial lithium salt. This is a pretty well-known, well-studied lithium sacrificial salt. It's been used in other studies. And so we were able to encapsulate this so that now we have loaded this lithium squarate inside these porous silica shells through wet impregnation. And then we can actually just start to put these into a cell. So this is first characterization. So this shows that through XRD and FTIR that we can actually tune the amount of lithium squarate that we load, and it's quite corresponding to our synthesis conditions. And then you can actually see sort of at the TM level, sort of these microcapsules and loading with the lithium squarate inside of them. And then when you do the electrochemistry, you can get a nice confirmation. Here with a standard cell, full cell graphite NMC622, and then here with the lithium squarate, you can see the decomposition is about 4.2, 4.3 volts, and lithium squarate decomposes to carbon dioxide, carbon, and lithium ions. And so when you look at the discharge capacity over time, you see that it's much more stable and much better retention over 100 cycles. And we're also really able to confirm that there is lithium squarate inside these things because we were able to do in situ NMR. And here we did it actually in a sodium metal system so that you didn't get confusing lithium signals from the other parts of the battery. Yeah, so that's been sort of the progress for our project. I know I didn't talk about everything, but I think it was probably maybe more interesting for you to see sort of the developments in our ups and downs. We developed both self-healing anodes and cathodes, but they're still, of course, work in progress. So the self-healing anodes, we've actually developed several polymer families with various tunable properties. So I think that's quite interesting. We have developed them primarily as films, and integration with that has been challenging, but we've been able to iteratively design the polymers to make them more promising for the future. For the self-healing cathodes, we actually demonstrated this improvement enhancement, and that's been published, and it's quite a nice system, but it's still, let's say, not necessarily considered self-healing. It has an improvement, but to really get this smart functionality as we would have to have something that you can trigger on demand and tuned that with, for example, some sort of sensor. So that's kind of our big challenge going forward into the future, is putting this together with a sensor inside of a cell and having that all work together with the BMS. But we still have a little bit of time left in the project, and that'll be our main target going ahead. We also have obviously learned a lot through all these challenges. We're hoping to collaborate with Phoenix and HealingBat. We're planning some self-healing webinars, and I think this would be good for the broader community to learn about sort of what the best practices are, what have we been challenged with, and also sort of the whole concept of self-healing, which needs, I think, a bit more definition and discussion through the community to really identify what that means and how do we classify self-healing and how do we decide what we call self-healing. So acknowledgements to, of course, my consortium, really good team of people that have held steady in the face of many challenges and headwinds. So thank you for their work, and also, of course, the acknowledgements to the funding agencies. We have a website and LinkedIn. You can follow us on there, and hopefully you can learn more about other things happening in our projects. Yes, I think that's all from me.
Thank you very much, Samson. So we can move to the next speaker, that is Dr. Joris de Hoek, senior researcher at the Bridge University Brussels and representative of the Phoenix project. Okay, Joris, you are muted.
Yes, I clicked the button, but it should be better now.
Yeah, now it works. Perfect.
Okay. Is the presentation mode fine? I think so, yes?
Yes.
Okay, so good afternoon. My name is Joris de Hoog. As Leonard mentioned, I'm indeed senior researcher at the Vrije Universiteit Brussels, or Free University of Brussels. I am the project coordinator for the Phoenix project. My discussion today is mostly going to cover our, let's say, strategic developments and the planned interactions. But let me first paint you a picture of what we are doing with Phoenix. So Phoenix, we're really trying to explore or to develop systems that are capable of interacting with each other, namely sensing, so battery degradation sensing, self-healing systems that are triggered, and a battery management system that oversees the entire operation. So apologies for the very blurry version of this picture, but this is the overall concept that we are developing at the moment. So you can see on the sensor side, we are working on acoustical sensors, we are working on thermal sensor, pressure sensors, gas sensors. Triggering of the self-healing functionalities is done by applying pressure, magnetic forces, and heat. And the self-healing is on all aspects of the batteries except for the separator. So we have developed or we are developing systems for self-healing on the cathode side, anode side, and the electrolyte in order to prevent the traditional degradation phenomena that we all know. So the polarization of silicon anodes, for example, the formation of dendrites, oxygen and gas evolution, etc., etc. So this is the overview of the strategies that we have in place and that we are currently developing within the project. So we are 18 months from the project deadline, so we have still some time. And as you can see, we are working on two different types of, or let's say 3 different types of batteries. So we are working on the traditional graphite versus NMC with liquid electrolyte batteries. So these are considered to be generation 3B, where we're mostly looking into avoiding structural changes on the cathode with high nickel contents, and the pulverization on the cathode. Then we are also looking into generation 3D cells, but with high silicon contents on the anode, where mostly we're looking into preventing plating and the evolution of gases, and then obviously as well the structural changes. And then finally, we're also looking into polymer electrolytes, so semi-solid state batteries with silicon anodes and NMC as a cathode. There we're mostly trying to combat the loss of active layer contact. And again, of course, because we're working with high silicon, we're also looking into the let's say, strategies to combat the structural changes. You can see the type of self-healing strategies or self-healing systems that we have. A little bit more detail is shown in this slide. So these are the type of self-healing mechanisms that we are developing. So on the anode side, with silicon anodes, we have developed a binder that is composed with magnetic nanoparticles inside, which we will trigger magnetically. So studies on this effectiveness are ongoing. We can also see that that this magnetic trigger might have to be combined with some heating as well. On the separator side, to limit the gas formation, we are developing a metallic organic framework. And on the cathode side, we have this NMC90 core shell structured with cathode microparticles to combat or to try to avoid mechanical degradation on the the cathode side. And this is then done with this this is an autonomous triggered self-healing system. And then on the electrolyte, on the polymer electrolyte, this one is fairly typical. It looks a little bit like what Samson has showed before. It's a polymer-based electrolyte that is capable of healing itself while it's heated slightly, so not too much, of course. Okay. And then on the strategy, because of course we have sensors, we have self-healing materials that are triggered by some sort of an external stimulus. So we need something to control this, because we are basically working on a system that is able to measure some type of degradation. It has to be quite specific on the type of degradation that it's measuring, because we need to apply very specific actions, or we need to apply specific stimuli for the self-healing to take place. So that's why we are developing a integrated BMS, where you can see that the BMS is responsible for detecting the degradation via the sensors, and then has to decide basically what type of degradation is seen, and then also what type of trigger is being applied to the self-healing. And so for this, we are counting on developing a BMS that is capable of doing the algorithmic calculations on board, using, of course, the sensors that are integrated in or on the cell itself, triggering the heat or the magnetic field that is, of course, built into the package of the battery system or the battery cell itself, using as best as we can off-the-shelf hardware to keep costs down and to make the system, let's say, commercially viable to a certain extent, of course. So that's a strategy. We're not done yet. So we have, of course, some future work. For example, our material development is not fully finished yet. We are optimizing specific things like the in situ cell triggering, because at the moment we are triggering this while the cell is stationary, but we would like to see, let's say, in operando triggering of self-healing, and to measure the effects of these. Also, the trigger systems at the moment are external, but for example, the heating pad that has been developed will be integrated into the cell packaging itself. And we believe that with combining all of these systems, we can achieve some kind of a balance between trigger systems and self-healing via the BMS, and ultimately aim to expand the lifetime of the cell itself, because of course that's what we are aiming to do with this with the self-healing project. This is the consortium. We are very happy with the collaboration that we have, yeah, that's it. This is me. If you have questions, don't hesitate to ask. We have a LinkedIn social community, as well as an online platform where we publish news articles, etc. in progress. So feel free to come and visit. Thank you.
Thank you very much, Joris. So I will check if finally Spiros has connected. No. Okay. No. Well, we can start the second roundtable discussion. So, does anyone have any question for the different speakers, or would like to comment on any aspect of the different talks? Okay. Yes, Joris, please.
I have a question for you, Samson.
Yes, go ahead.
So Samson, you talked about this iterative design of the polymers. Could you explain how you are managing this within the context of like your project? Are you working on this with multiple partners at the same time, or is this one single partner that is measuring, adjusting, measuring, adjusting?
Yeah, it's taken quite a few cycles and discussions, but most of the polymers are synthesized through our partners in Spain, Polymet, and a startup, a small SME there that's focused on synthesizing polymers. And then we've had input from our side, let's say the anode team and also the cell team working on a full assembly. So we've had anode team at my institute, also at University of Oslo, and we've had these meetings back and forth, and we also had to arrange actually some visits, physical visits, and like to discuss sort of the challenges and actually have some brainstorming, because you can only do so much in, like, let's say an online 1 or 2 hour meeting, and sometimes we have to spend like a day and a half there, and actually of course got to visit the facilities, but we had to do this quite early on in the first year of the project, because even then it was a bit challenging to really understand. From our side, we don't have so much organic chemistry experience, which is really the key deficiency on our side. And then they have lots of organic chemistry experience, and getting those to meet together, and also with different situations where we're sharing results. Electrochemistry side, they do a little bit of electrochemistry also in Spain, but obviously we're doing much more, and we're much more experienced than that. So it was difficult. I would say it's not simple, but we had to push for more bilateral meetings, let's say, or trilateral meetings with several partners, and yeah.
No, thank you.
Yeah, data sharing. I would say data sharing is really important. Yeah.
Okay. Yes, Colin.
Yes, thank you for the talks. I got a question maybe for the self-filling projects. I discussed a lot about these sensors during the last years, and there are, I would say, kind of critics that always come back that if you want the internal sensor to be useful, then you have to put them in every cells, and then it's a lot of cabling. And then it could be a problem also for the pack and the construction of the system. How do you foresee that? Do you think you really have to cable everything, or do?
I think from our side, our primary development on sensors has been more on compatibility and encapsulation inside the cell. I think we would plan to have a sensor in every cell, but we would probably only have one such. It would be like one sensor unit, which would have all of the kind of cabling together. So we wouldn't have it would look like a single cable. But we have actually, I think, some sort of design where it would all kind of be together, but we don't have as many. I think maybe Phoenix might have more sensors than we do in terms of our design. But you can speak to that, of course. Yeah,
we do, and it's a very good question. So it's okay. So a couple of things. So in Phoenix, indeed, we are developing and testing quite a lot of sensors. However, we are not, let's say, aiming to integrate all of these sensors in the cell at the same time. So part of the study is to do some kind of a sensitivity analysis and cost-benefit analysis on what type of sensor would be most beneficial to be built into the cell for actual integration into a commercial system. And that is, I mean, it's cost effective, but also useful for measuring some type of degradation. So this could be like a third electrode, because we're also developing this third electrode, or it could be a pressure sensor. If we're talking about pressure sensors, then I'm not sure if it has to be one sensor per cell, because if your cells are packed next to each other, you will measure the entire pack movement, not individual cells. So that is something to be considering. Then I probably would say that it doesn't make sense to have a integrated pressure sensor, but have, let's say, one string response, or like one sensor per string or something like this. But indeed, every additional wire, every additional connection is one potential point of failure for a battery system. So the choices need to be made very carefully. I mean, we are developing, for example, thermal sensors that are integrated into the battery cell. When I'm speaking, like, this is very interesting from a scientific side, because then we get insights from the inside of the jelly roll. But very practically speaking, or if I'm looking at this with the eyes from the industry, I would not be interested in this technology, because, I mean, if you can measure the temperature on the outside of the cell surface, it's good enough, right? And then we don't have the issue with the encapsulation, with sensor wires that are sticking out of your encapsulation. So it's a trade-off. This is a very low TRL project at Phoenix, so we are less concerned with, let's say, these practical, real life considerations. But of course, it needs to make sense, and so that's one of the outcomes of the project that we aim to have, or that we aim to deliver, is to make this analysis and to show what sensor systems make sense and which don't.
Okay, thanks a lot. Very clear.
If I can just add on one more thing to that, I think one of the interesting developments from our side is that I think sensors, the wiring is manageable. The difficult, actually, challenge that we didn't expect is probably the BMS. Need to handle the amount of sensor inputs, like the amount of data coming in, and that actually takes up processor time on the BMS. And so now you have to balance sort of, if it's measuring like 3 sensors or 3 inputs, and also measuring, current voltage and all these other things, that like you have to time it so that you're actually able to efficiently measure and receive those signals in the right time, and not occupy the processor for too much time, is a very deep computational or like electrical engineering aspect. But I think it was an interesting, unexpected challenge as a battery scientist, to see that the BMS would be so preoccupied with so many sensor signals, like frequency of measurement and all this, I think.
Okay. Perfect. Let's go to Carol, that has raised the hand. Carol Frolit from CIMIA.
Yes, thank you, Leonor. I will have question to Dr. Colin regarding protective coatings by ALD. What is your experience? What is improvement using these protective coatings, and what is potential industrial application? Can it be this technology applied for battery?
Yeah, so the ALD, the big advantage is the conformal coating you can get from that on a powder. So it's really important, if you take a look at an interface cathode electrolyte, if there are spots where there is no coating, then you have weak spot in the interaction, and you can start the reaction there. So that the big advantage of the ALD, and what we want to prove in the project is that we can upscale this process. So we know at the moment it's not something that it's easy to do, but the idea is really to produce this kilogram scale material with the ALD, show that it's feasible in a, I would say, economical, sound way. There has been already one startup that tried to commercialize ALD process. It was NanoForge, and sorry, there was a first study that showed that for a cathode material, it would be $1 or $2 more per kilogram. So if it brings more safety, more stability, that's a cost that you can go for.
Okay, thank you.
Okay. So we have one question from the chat, and then we will go to Mesfin question. Okay. From Esha Canwell, when integrating recycled graphite with silicon additive in Gen 3 anodes, what strategies are being explored to balance mechanical stability, say integrity and sustainability targets, especially given the higher reactivity of silicon during cycling? I guess that this is directed to Ulla. Correct me if I'm wrong.
Yeah, actually, probably not, but because actually we are not using in these big cells at all the silicon. So silicon is only in the laboratory scale. But with the recycled graphite, we will reuse it, increasing some of the conductive agents, which are also this kind of recycled element, and then. Yeah, that is our anode chemistry. We are only doing carbon silicon composite in the laboratory scale, but not in the big scale. So probably I don't know if it was to me, but I cannot answer because we don't have this kind of like a big cell testing data available. And I'm also cathode research by myself more. But if someone else can comment on that.
Okay, thank you, La. Let's go to Mesfin.
So it's a general question I have for those self-healing projects. My question is, how far are we now from getting this smart self-healing process or battery or whatsoever? And what's really the bottleneck there to have this smart self-healing?
Can I? Wait, I'm sorry.
Go ahead.
Were you going to say something?
No,
okay, so
no, go ahead.
Okay, so I will give a very candid, frank, personal opinion here, and I will preface it by saying that this is not necessarily shared by everyone from my project from Phoenix, but I think we are quite far from a, let's say, commercialized self-healing smart battery. Why? Because commercial LFP batteries already cycle 10,000, full equivalent cycles before they reach an 80% SOH. I just come from a conference where it's called Zero Emission Busing in Brussels today, where they were talking about life cycles or lifetimes that they are seeing in electric buses using NMC batteries, and these buses that were taken into usage in 2017 have reached the battery packs in these systems have reached their end of life after 1.75 million kilometers. So that's what I think is going to be the bottleneck for commercialization of self-healing systems. The fact that actually batteries are already lasting a very long time. So it's a question that I have maybe to give it back to somebody else. I think this is technology that is meant to be developed or to be deployed for very specific use cases. Very specific use cases where batteries are supposed or where there are requirements on extreme lifetimes and where battery replacement is not an option. And then I'm automatically thinking about systems, for example, for the aerospace context. But there, I think maybe their energy is not that big of an issue. I'm not sure, but it's a question that I'm bouncing back to the rest. Like, what are you guys thinking of when it comes to applications and commercialization potential?
Yeah, yours brings up a lot of good points. I've been mostly focused on just like project deliverables and things. I think for us, the challenge has been really proving self-healing, I think, to show that it actually works in the way that we intend it to work. And as a concept, we have this description of what it should be, which is that it should be activated, it should be intelligently decided, and these kinds of things. And I think there's just so much parameter space that you have to explore with self-healing that I don't think we are not really talking about or have any sort of standard way of talking about, like, when do you self-heal, like benchmarking, like, if you have degradation in the first 3 cycles or the formation cycle, is that when you should be self-healing, or should you wait until you're at 80% capacity health, right? And then that's okay, now we can start to activate self-healing, and understanding that is optimizing that, let's say, it's really difficult. Getting the sensors in, I think there's been work on sensors already, so that's more of a mature technology in my opinion, so that's kind of there already. But in terms of a smart cell, how far away we are, I don't know. I mean, certainly the manufacturing is much more challenging probably than we can anticipate in terms of integrating those cells and the sensors and those kinds of things. We want it to be as easy as possible, but of course, just the basic challenges of putting something foreign, new into a battery and kind of needing to validate that each time you add something new. It's a very ambitious project, and so I don't know. Yeah, it's but I think yours does bring up a good point. Where do we see this as an application? It's I don't know. I mean, maybe you can argue that it's more intended for other chemistries that have more specific degradation mechanisms or more aggressive degradation, and you want to kind of, rather than try to spend the time to optimize their lifetime, that you develop a self-healing that counteracts them. So like something like silicon, which is fast degradation, can you counteract that, or something with high manganese, and there's a lot of manganese dissolution, or pre-sodiation, pre-lithiation, something like that, where you can heal that. I don't know. I mean, of course, then you have to do cost benefit versus, is it better to just buy a lot of cheap LFPs and make it a bigger system or something like this?
Yes, Joris?
Yeah. So exactly. So what I didn't mention in my monologue just before was indeed, I'm talking about let's say, the commercial viability for current generation and let's say 1 generation plus type of batteries. If we're talking about pure silicon anodes, for example, there I think it makes a lot of sense to develop self-healing, or at least these binding systems that are self-healable for silicon anodes, because we know that these are really affected by volume changes. So there I think it makes sense, but we are not there yet. So to give you an answer to your question, Mesfin, in terms of commercialization, I think we will see the first commercialized self-healing systems that might not be smart but might self-heal when high silicon anode systems are going to become available. Because I think this will there is a potential that these are going to be one cannot exist without the other, maybe.
Thank you.
And following this line, so right now self-healing is being researched at component level, or have we achieved cell level, or just a component right now?
I think for us it's mostly component level. Yeah, so just trying to get the well, I guess, on the cathode side you could say that maybe it's a cell development, but then it's a question of, is it really self-healing? I mean, this is an existential question of like something that obviously has better capacity and improvement, but it immediately happens on the first cycle. So that that lithium squarate is active already. So if it was something that like you wanted to wait, I mean, there's not necessarily a good reason to wait maybe for lithium squarate in that case. But if you had something else like a manganese ion scavenger, for example, there's not going to be manganese dissolution in the first cycle necessarily. That might come up later, you know, like 100, 200, 500 cycles later. And then you want to actually try to maintain or improve the lifetime there. So then you do need some sort of activation. And then we don't have that yet, let's say, on the cell level. We have it maybe working on it on the component level, yeah, but not on the cell level.
Perfect. Okay. Yes, Leif from Serpotec.
Yeah, hi. One possible commercial use might maybe be pacemaker batteries and other medical implants where you really want to replace the battery as seldom as possible.
Yeah, indeed. Yeah, that's what I mean indeed with these hard to reach devices. But indeed, yeah, in bodies are also typically hard to reach, especially on the inside. So yeah, it makes sense indeed. Yeah, thank you for the suggestion.
You can also imagine, especially on the sensor side, any sort of application that's very critical. Early detection of potential failure before failure happens is a really good motivator, let's say. Kind of like, it's almost like a non-destructive test or non-destructive sensing to be able to anticipate failures before they happen. And that's where sensors, at least, would be really, really powerful. Of course, then you can combine that with self-healing, but sensors, at least, would be really helpful for critical applications.
Is there any target or quantification? Maybe not, because we are in a lower stages of maturity, but is there any target or expectation that we have around how cell healing can extend the lifetime of batteries, or not, because it depends on where it is applied?
So for Phoenix, to give you a very straightforward answer, we are aiming with all systems combined, or at least with the system that makes most sense, for twice a lifetime. So at lifetime times 2.
Yeah, I forget exactly what our KPI is, but probably something like 50% of our lifetime. And there are some KPIs related to specific sensors and what they would detect. So like manganese ion dissolution concentration, for example, and it's more focused on that, or change in resistance of the anode. If we expect more cracks there, then it should reduce the amount of cracks or maintain the adhesion better. But I forget the exact performance KPIs, which are always really ambitious anyway. So.
And are these systems applied on new materials, no new raw materials, or it is also valid for secondary raw materials? So did you test or try to do that in recycled material? If we can recover it with this kind of...
That I haven't, I don't think we've really tried. We are looking at the recyclability of self-healing and recyclability of sensors and how that might affect downstream. But we haven't looked at using, like, combining with recycled materials. Wasn't really in the scope. Would be interesting, actually, to see. That's where maybe you can say there's some issues that you might want to be able to resolve. If you know the degradation mechanism of recycled materials, that could you add something in to sort of help compensate for it as it happens if it's a slow process or something.
It would be nice to have also that on mind. Okay, so I guess that most of the projects that are in this session are already in contact and have their own collaboration in place. But well, if you would like to say something in that respect, if you will have in mind and any activity, collaboration activity between the different projects. For example, in the full map project, Mesfin, correct me if I'm wrong, we will need also to have some data about self-healing if possible. So I think that we would like to start different collaborations, and of course coming to the, I don't know if it is the main announcement of the workshop, that is sharing data, how to share the data between the projects and so on.
We have gotten started a little bit in terms of like trying to update the ontology, the battery ontology, to think about, okay, now we had binders, we have conductive additives, we have active materials, but there isn't a, where do we put the category of self-healing material somewhere in the cell, right? And you would want to know in any battery cell that you've tested the metadata that, oh, this has this material and it serves this purpose, right? And it's not a binder, it's not necessarily conductive, but it's there. And you want to be able to understand how might that affect the performance of cell compared to one without. So we have looked at sort of what type of information would we need to store in the metadata, and how should that information look? So we've gotten a little bit started with that, but it's still very early stages for us, I think.
Yeah.
But we are thinking about that, I think. And then, of course, what metrics? This is the difficult conversation, I guess, that we want to have with the projects. What metrics are important? What data of self-healing? How do you measure self-healing? And how do you quantify that as the data? And then have some sort of standard way of that. That's really difficult because, of course, self-healing is a big, right? You have so many different types of self-healing that we have talked about in just our two projects. And there's a third project, of course, that has, and then the different chemistry systems. So that's a challenging thing, but I think, of course, it's important to have that kind of conversation to get started on some agreement of a standard of what self-healing is. And the same thing with sensor data, right? So if you're going to make cell cycle ability, what is the sensor data telling you? And then, of course, you want to be able to correlate those kinds of things, right? Look for that. And then how is that sensor data, how should that be also ontologized, or how is metadata around sensors? I think that's probably very underdeveloped at this point. But this is the time to start thinking about it, right? Before
yes,
when the field is kind of young, and then we can actually have these conversations and build it correctly from the beginning.
Yes, for sure. This is the aim of the workshop. So thank you, Samson, for the suggestions and for your answer.
We could definitely collaborate more on that, I think, especially with full map. Yeah.
Do you want to say something else, or you want to comment anything, or have more questions for the speakers, or to discuss here? Okay. If not, we have now another comfort break in our agenda. And well, let's see you in 10 minutes, if it's okay. So for the last session, focus on manufacturing, digitalization, and circularity. So see you in 10 minutes. Thanks. Hello, everybody. Welcome back. Okay. Well, now have passed 10 minutes, so we can continue with the session. Specifically, we can go through session 3, manufacturing, digitalization, and circularity. This session links the downstream phases of the battery value chain. So it groups digitalization for manufacturing, as it is done in BATT4EU project, with the core circular economy projects like BATMAS and reuse. So the discussions can focus on how digital tools connect high yield production with efficient end of life management. Okay. So I would like to introduce the first speaker of this session, that is Dr. Ozan Emre Demir, Assistant Professor at the Politecnico di Milano and representative of the coordinator of the BATTERY project.
Yeah, thanks, Leonor. Can you hear me well?
Yes, we can.
Perfect. May I share my screen?
Yes, please.
I hope you can see it in the presentation mode.
Let's see. Now we can see the whole PowerPoint. Maybe if you go to the presentation mode.
I put it in the presentation mode, but maybe it's the same issue as before. Let me just share my entire screen.
Yes, you need to share the entire screen in order to do it.
Yeah.
Now it's perfect. Yeah.
Okay. So hello everyone. My name is Ozan Emre Demir. I'm from Politecnico di Milano, and I'm an assistant professor at Mechanical Engineering Department. I'm today representing the project coordinator Marcello Coledani, but I'm also working on the project as the project manager and the technical developer on the system level performance analysis. Today I will give you a very brief emphasis on what does it mean to achieve zero defect manufacturing in battery production lines, and specific characteristics that we are investigating in the BATTERY project. So I would like to start my presentation with an industrial motivation on why BATTERY is particularly important on the European battery manufacturers. In Europe, it is expected to establish 25 new gigafactories. So that was the gigafactory map, how gigafactory map is looking like in 2020, and now it is going to be it is changing constantly. Some new actors are joining to this map, so you would see more highlighted areas, or some partners, some industries are let's say falling down, so leaving this this map. Therefore, it's a very dynamic sector, as you may know. So a lot of battery cell manufacturers are opening in comparison to Far East. So main competition is, of course, coming from China, but Europe is also starting to accelerate its own development of battery cells, also module and pack assembly. So this is how it is looking like for now. Maybe the dates are not the most updated ones, but yeah, since we are all inside of this business, we know how the things are evolving. So of course, when new factories are establishing, it is very typical that you generate more scraps than the steady state production. So according to the analysis coming from Fraunhofer FFP, the typical defect rates or the scrap rates are around 30 to 10%. So it's not negligible, let's say. So what happens is that when you are producing this many scraps, of course, it has and also economic drawbacks to your business plan. So we have seen, for instance, in the case of Northvolt, they basically could not handle and manage the production ramp up, and they were constantly producing scrap units. And of course, this is due to the lack of know-how in Europe, but also it's the complications that may arise during the ramp-up phase of any production system. So it's a very dynamic sector, and a lot of new actors are joining. Some actors, unfortunately, are leaving. So what are the equilibrium points? What is the equilibrium point in this context, and what are the implications, or on the contrary, opportunities for battery manufacturers? So, as we well know, the battery manufacturing system is characterized by three different material flows. So we have some process, particularly mixing, is characterized by batches. or then followed by a continuous flow of materials in coating, calendering, drying, and until the separation phase. And after the electrode foils are cut in either slitting or notching, then we have the discrete part flow. So we start building the battery stacks and go into in the sealing and formation and aging process. So all this meanwhile, what happens is that the purpose in the ramp up management is to first anticipate the potential problems in the meanwhile. So it is basically to bring this point one that you can see on the right figure to more closer to the target throughput that you would like to achieve in the steady state production. So that means you are reducing the cumulative throughput loss in that area, in that red area. Or the second strategy is that by using the data analytics or the knowledge that we have from the previous experiences in this ramp up phase. So the ramp up time on the right side, noted as blue 0.2, is coming closer to the left side. So the whole idea of managing ramp up is to reducing this red area that is essentially the loss of production. So the BATT4EU is trying to support in that field the future gigafactories, how to handle this defect generation and then propagation during the ramp-up phase, but also during the steady-state production. So where zero defect manufacturing becomes particularly important in this context is that zero defect manufacturing is slightly different than the traditional quality control mechanisms such as total quality management or lean management, Six Sigma, however you would like to, however technique you would like to use. They are mostly concentrated on defect detection and the correction. So you mainly work on feedback control mechanisms. Instead, the idea of zero defect manufacturing is to identify on the spot what has gone wrong, although you may be still within the control limits and your, let's say, part is accepted in the quality control, it may still generate some problems in the downstream processes because of accumulating deviations. Therefore, the zero defect manufacturing looks at the trends in real time and tries to correct what has been going wrong or slightly different than nominal in the downstream production. So you work more on the feed-forward controls. So that is the essential differentiation of zero defect manufacturing with respect to the other control mechanisms. So in many, let's say many industries, the products are getting more and more complex. So the number of variants and the features that a product must include is getting enormously high. Of course, the customization and the personalization brings us the challenge of constantly adapting processes or the production systems in some cases. And of course, we need to have a certain level of traceability. We were talking about DPP, for example, in the on-site meetings today. So this brings the understanding of how what is the characteristics of a product and which phases it passed throughout its life cycle. So that's why ZDM is getting more and more attraction in the last years towards ramp-up management. So essentially in BATT4EU, what we try to do is to develop a digital twin platform supporting this digitally enhanced ZDM approach for the European battery manufacturing industry. The coordinator is us, Politecnico di Milano, but we have 16 different partners, many EU member states, and now 2 UK partners as well. So I will talk about this whole let's say, framework in the next slide. So how we are trying to achieve this level of complexity is that basically we collect a lot of distributed multi-source data from integrated sensors or the monitoring mechanisms. And we bring all this into a singular data management platform. So this data management platform ingests all the heterogeneous data from diverse resources in a different format, and lets it makes them usable for the process level digital twins. So at the process level, what we typically have is that multi-physics models of each singular process. It could be related to mixing, it could be related to coating or calendaring or stacking or tab welding or notching. So anything that you can imagine in a battery manufacturing line is represented by a digital model in that sense. So if these digital twins are able to be used in the real time, so maybe the computational time is not that heavy and they can be directly used, we continue to use in that way. If not, we apply some proper order reduction techniques to extract the core of the model, let's say, core of the digital twin. Instead, at the system level, what we have is that state-based resource models. So it could be something related to machine, or it could be also robotic handler. It could be the conveyor belt, anything, any resource that is existing in the production line. Discrete event simulation or the approximate analytical models to estimate the performance of the battery line. So here we take a look at the KPIs such as the total throughput, so how many parts have been produced in a certain time unit, or what is the conforming portion of these total production that is called effective throughput, or such as work in progress and the quality metrics. So they are connected in the multi-objective optimization to enhance and predict and enhance the overall system performance. So this connection between process level and the system level is particularly important in BATT2In, because we are not only trying to connect different inputs and outputs of each processes horizontally, but we are also trying to bring this information at the system level to understand what changes and improvements have been made at that level has an impact on the system performance. So then we can decide as the production managers whether to invest in or not in these technologies. So one of the questions, as I mentioned, we are looking for is that how to interconnect these inputs and outputs of each processes to formalize the defect, deviation, and aggregation patterns, so that when a new ramp up is happening, we can already use the existing knowledge. Second, how can we manage this distributed heterogeneous data that are coming from multiple sensors? What is the impact of developments at process level on the system level performance in terms of productivity, quality, or the logistics? And how to, of course, integrate these diverse tools into a single platform with their unique workflows. This is particularly challenging because of course, each model has been developed in the same environment. So some of them are coming from COMSOL, some of them are coming from MATLAB or ANSYS Workbench, whatever. So they have to be somehow integrated into these user-centric workflows to achieve certain results, such as process adaptation or the production system design, production planning and the control, etc. So these are the questions we would like to answer. I'm just going to give two very short examples of what we are achieving in the meanwhile. So we have these decoupled models. and we are performing an input-output compatibility study. Then we interpret the model, unify, and in case needed, apply proper order reductions or meta-modeling techniques. Then we go into interfacing, integration, and validations. So in the stacking example, so what we have at the beginning is we are trying to invest in predicting the performance of the battery after the stacking based on the defects and deviations coming from notching and during the material handling. So here we have the gripping reduced order model. So when the vacuum gripper picks up a flexible component, in this case the electrode foils, anode or cathode sheets, picked up and placed on the stack, of course the vacuum gripper applies a mechanical stress that might deform the sheet while bringing and handling the material into the stack. The second is that the robotic model, which is representing the pick and place robot. Here we are taking a look at the positional accuracy. So even if everything is flat and perfect, there will be some kinematics error coming from robotics. Therefore, we would like to also understand how these two can be combined. And we are trying to use this knowledge into feed-forward controlling of the desired trajectory of the robotic arm. So, of course, if we can estimate in a certain level of accuracy the deviation of the deformation of the sheet and displacement in the stack, then we can use it to calibrate our trajectory and you apply a feedback control to the actual trajectory. The second is when the electrode sheets are placed on the stack, of course, a pressure must be applied. And here we have the material model that is modeling the compression phenomena. And also then afterwards, the stacking machine robotic model. So how these actuator forces are applied. And then this could be used for state and disturbance estimation. So the state of the integrator, estimated robotic trajectories, etc. So we are trying to connect the first part until the material arrives to the stacking machine and what happens during the actual stacking. On the system level, instead,
Ozan, excuse me, but the 10 minutes have passed, so if you could...
yeah, I'm just wrapping up. Okay. Yeah.
Perfect.
So at the system level, we have, as I said, approximate analytical methods that are more about the mathematics of the small portions of the system. And on the other side, the discrete event simulation. So we are using analytical methods which are faster to pre-filter some feasible scenarios, and discrete event simulation to go in more depth analysis in the multi-objective optimization workflow. So what I'm trying to say is that, of course, there are many research involved in battery manufacturing, but they are mostly isolated, targeting single stage. But I think we should start thinking about more integrated solutions, also including the system level that completes the perspective of product and the process models within the control architecture. So if you have any questions, I would be happy to connect during the workshop, and please feel free to reach out to me for more information. Thank you.
Thank you, Ozan. Thank you very much. So let's continue with our next speaker, that is Mr. David San Juan, Senior Project Manager and Policy Officer at the Iberian Sustainable Mining Cluster and representing the BATMAS project. Please, David.
Hello, can you hear me?
Yes.
Okay, let me check. I will try to... Can you see the presentation?
Yes, perfectly.
Okay, so thanks, Eleanor, and the rest of the colleagues for inviting us to present the project. Actually, this project is also led by Politecnico Milano, Marcello too. So it's a pleasure. That was really quite interesting, the previous presentation by Ozan, and also the rest of the colleagues that were presenting the projects. For me, that I'm not coming from I'm not research, and also I'm not coming from the technical part. We are not providing outputs for the technical part of the project. We are more focusing on specific tasks on the policy landscape and also communication and clustering tasks. So it's quite important having this approach. So I will try to go quickly for the time. Okay. So why this project matters, no? So why this project was created? I think that we have to take a look about three different important aspects or axes that should be responded by the project and the rest of the project. First is the demand is increasing sharply. Electric vehicles and stationary storage are surging, and the European Union must expand by 19 times its battery supply on a massive scale over the next decade. At the same time, Europe remains highly dependent on imported critical materials, which expose our industry to volatility and supply risk. As mentioned before, with the college for the Politecnico Milano, the planned gigafactories in Europe are insufficient currently. And in other sense, connecting with sustainability and circularity is therefore both an environmental strategy and an industrial competitiveness strategy. High recovery and reuse, lower extraction, and a stronger regional value chain is quite important. Circularity stands as a way out. However, only 10% of battery materials is currently recovered, and only 1 to 3% of lithium gets recovered worldwide. That's the gap that BATMAS was designed to close and was created. Wait a minute, please. The project is co-funded by the European Interregional Innovation Investment Program. Is implementing by starting in September 2023, and actually supposed to finish in the middle of 2026, but we are expecting a formalization with the outputs of the demonstrator lighthouses that are in the final step of validation. The goal is a comprehensive ecosystem, the circular battery valley, that expand the whole life cycle. I mean, collections, second life, black mass recycle, and remanufacturing into new cells. The consortium mobilized an interior network, which is quite important, around 40 demonstrators lighthouses that scale technologies to market and the risk investment. The consortium is composed by 15 partners coming from 4 member states, but quite important is taking over look on the regional levels involving 11 regions, combining industrial players, research and technology organizations, cluster and regional actors, which is quite important. This mix covers the full value chains from logistic and dismantling to the second life to the metallurgy and manufacturing. So the results to bankable projects. Taking a look about the demonstrator lighthouses, is close the material waste to production loop. The Valley relies on collaborative approach to the triple helix, but also the engage of investment community with the ambition to scale and replicate innovation strategy to European Union resilience. This is the image that I will try to explain a little bit about what is currently the demonstrators. The first demonstrator, which is led by ERP, is focusing on advanced logistics for battery recycling. The demo deals with one of the biggest bottlenecks, which is how to move used batteries safely, predictably, and legally across borders. The partner is currently standing up a digital operation platform and rolling out training models, starting with end-of-life rules, extending procedure responsibility and reach. Also testing safer packaging and a safety sensor box. It's also specifying a fire control safety box and associated sensors. When the integration point is final, the sensor will be procured and implemented. In the second demo, which is focusing in giving a second life to batteries, is led by EnviroBAT and also Visions, but it's all about reuse testing and building energy storage systems using vehicles batteries. The market is especially in residential solar eager for these solutions, and the feedback is quite positive coming from the technical partners, driven by the cost advantage of Second Life systems. The test bed is operational. They are preparing with key indicators for evaluating the Second Life application of automotive batteries. Portable, medium, and large systems are moving through the development and use, and they are enriching by photos and explanation highlighting the specific features from the technical part. No. The third demo, which is focusing, sorry for that, the third demo, which is focusing on recovering raw materials from black mass, is for turning black mass into bankable materials, the step that extract lithium, nickel, and cobalt. The process is technical mature and already running, but the project is facing two big challenges that we will try from ESMSA to convert it into political practice for the regions. That is finding the right balance between high purity and high recovery. And secondly is the feedstock leverage. That is quite important. And the fourth demo, which is leading by Baricor, is testing new generation batteries using recycled materials. It's closed the loop by feeding recycled materials into PCM and CAM and validating new cells with recycled content. The partners are now validating how much recycled content can be used while maintaining the performance. But the economics, the economics are still fragile. Recycled materials are quite expensive, and there is no clear EU demand signal from recycled content. And all of this is going to be related, is in the final step of the project and implementation leading by Enable into a circular battery valley, which is on the way to create an association that keep partners connected beyond the project, one-stop ecosystem that support new investments with a sustainable business models based on membership and services. Is good. The circular battery valley will implement it by different services or experience coming from, for example, matchmaking among companies, regions, and investors, capacity building training models, and also investor pitchings to accelerate market uptake. The final goal is having like a long-term structure that continues beyond MATMAS to make these demonstrators, lighthouses, investable and replicable across European Union, but also external. And it's remaining integrated by the European Union partnerships, for example, the thematic smart specialization platform of advanced materials, raw materials partnership, etc. So this is what sorry for that. This is what from ESMC we're trying to analyze. Is the challenge is not the objective from our side, is how is going the implementation, considering that there is several EU regulations that are affecting the implementation of these projects, coming from the battery regulations, critical raw materials act, net zero industrial act, but give a strong demand and supply side signals. But this only can be successful if it's not, we are not only taking a look about European level, but also national, a completely regional and local level. The regions can deliver common outputs, capacity plans, safe logistic, harmonized procedures, and also having embedding that with the going debate of the future budget of the European Union, how this smart specialization strategy can be integrated with all the know-how and the technical output that are coming from the batteries projects. And also taking a look about integrating the resilient clauses in the public procurement. In many countries, especially also taking a look of Spain, they're focusing in the criteria of price to select operations. So it's important boosting and having an overview about the green impact, but also social impact of this demonstration experience. So it could be quite expensive, but having quite important, like having a global overview about that. No, wait a minute. And for the political practice area of the EU investments, sorry for that, we are taking a look about the different barriers that demonstrations are facing. First is make cross-border transport predictable. Recycling can scale if we cannot move batteries, and needing a one predictable approach and fully digital notification that remove friction and keep safety high. And second, ensure interoperability with digital product passports and apply GDPR proof data governance. The goal is interoperability, not new closed systems. Third, create a European Union framework for Second Life, establish common certification and testing for reused batteries. Markets want a Second Life, but rules lack. Sharing EU certification and testing path, clear liability and insurance. This also helps the risk of automation and safety upgrades, which is quite important. On second part, improve the safety and consistency across the chains and the risk projects. Use blended finance and provide the state aid clarity and ensure affordable energy and grid access for recyclers and reusers. As we mentioned before, this is a huge challenge with the high purity expectations and regulatory law that increase the cost. We need a competitive balance that still meets environmental ambitions. And finally, what's great about the technical part, the technical projects, technical partners, etc., is how this circular valley platform could be useful to integrate this know-how and pushing with the regional level and public frameworks to integrate these perspectives. So that's all. Thank you so much for having me this opportunity to explain a little bit about the project. You can contact directly with the leading partners and those partners that have the technical overview of the project. So it was a pleasure.
Thank you, David. Thank you very much for the talk. So let's continue with the last talk and the third speaker on this session. That is Dr. Andreas Bittner, that is CEO of Celsius and representing the Reuse project. Please, Andreas.
Many thanks, Leonora.
So now we are seeing your full screen. So
I try to come to presentation mode. Now it works.
Perfect.
So, hello colleagues, my name is Andreas Bittner from the battery recycling startup CellCircle, and today I will give you a short introduction into our project Reuse and our sustainable direct recycling of LFP battery waste. Reuse is a Horizon Europe research and innovation project that started beginning of 2024 and has the goal to reach a TRL of 4 or higher by end of 2026. Which means that our innovative processes are validated at least on lab scale. The focus of Reuse is the next generation of battery recycling called direct recycling. And in contrast to the standard metallurgical recycling, we are not disintegrating the battery materials into the elements, but we are recovering the battery active materials destruction-free to directly reuse them for new battery cell production. And benefits are that we are able to recover all main components of LFP batteries, we can minimize the carbon footprint, and we are enabling closed materials loops, as you can see in the illustration on the right hand. The big goal of Reuse is to develop sustainable, low energy and scalable processes for LFP battery recycling to ensure high recycling efficiencies and high purities of the recovered materials to be able to use them for the battery cell production and to fulfill and overfulfill all future requirements of the EU batteries regulation. And to make this possible, we are developing automated end-of-life battery sorting processes. We are developing automated battery cell disassembly processes. Then we are developing efficient separation, purification, and regeneration methods to recover ready-to-use battery active materials, carbon black, binder, and also the different electrolyte components. And to ensure sustainability, we also have a work package that is fully focused on life cycle assessment, life cycle costing, and also social life cycle assessment. And for Reuse, we have a strong consortium with 13 partners out of 8 European countries that are covering all edges of the knowledge triangle: industry, research, and education. You can see the logos of our partners on this slide. The project is led by the parent institute of our startup, the Fraunhofer IC, and our company, Cell Circle, is one of the key exploitation partners. And with my next slides, I want to give you a short overview of our key process steps in reuse. The first step is the battery preparation. And herefore, we are working on AI-supported sorting processes to extract LFP battery cells out of battery cell mixtures that include, for example, also NMC cells. Then we are working on universal methods for discharging that are not harming the materials, that are cost efficient and scalable. And we are working on new deactivation methods, for example, in protective atmosphere to make sure that we have no exploitation, to ensure that we have a safe handling of the batteries. The nice example of our battery sorting is the AI-based sensor platform of our partner Vito with X-ray sensors, color sensors, shape sensors that are able to separate the LFP cells out of the mixtures. And we've trained this system with 18650 round cells. On the right hand, you can see that we already have achieved a successful separation and detection of the different cell chemistries. The next step is the disassembly and the material or component separation. Herefore, we have two routes. The first route is the automated battery cell disassembly that includes the opening of the battery cell housing, the extraction of the electrode wraps, and then the delamination, the unfolding of the electrode wraps. The second approach is a material selective shredding with an adjusted shredding configuration that enables the recovery of anode concentrates and of cathode concentrates to also use the shredding approach for direct recycling. And both of these routes include also the recovery of the electrolyte solvent and of the electrolyte lithium salt, LiPF6. A nice example by Fraunhofer. The first step in our automated cell disassembly process is the opening of the battery cells and the extraction of the electrolyte wraps. And you can see in focus 1, the cutting line in green that is automatically adjusted when the cell is moved. Focus 2 shows the second step, the extraction of the electrode wrap out of the compound. And herefore we have to cut the connection between the copper and aluminum current collectors and the respective aluminum and copper pads. Also here you see the green cutting line. And focus 3 then shows the last step, the cutting of these small glue stripes to be able to unfold electrode wraps in subsequent steps that are also automated. An example for the alternative route is shown with a lab scale shredder that was developed by our partner DTI. And on this scale, we are able to adjust the configuration of the shredding very quickly, very cost efficiently to really separately recover anode and cathode materials out of the shredder. On the right hand, you can see the design of the system. So it includes a closed system with an inert gas atmosphere to ensure that we have no explosions, to ensure that we can also recover the electrolyte, and to ensure that materials are not harmed in this system. Third step is the delamination, extraction, and purification. Here we have an electrode delamination based on a liquid approach, for example, delamination with water. And this enables very high recovery rates, very high purities that are needed for the direct recycling. We also work on electrolyte recovery with solvent extraction and vacuum distillation approach. We are recovering binder also via solvent-based approaches, for example, in a SOX-led process, optionally supported by ultrasonication. And last but not least, we are even able to separate the active materials from the carbon black with a semi-continuous centrifugation process. A nice example is shown here from our partner Keyboards with a water-based delamination for different types of battery waste electrodes, either from production scrap, from reject cells, or from end-of-life batteries. And on the right hand, you can see we have achieved a complete delamination with very clean aluminium and copper current collectors, and also clean cathode fractions that are delaminated respectively. The last step in our process chain is the materials regeneration. So we are regenerating both the cathode and the anode materials. And for the cathode active materials, we are using microwave-assisted hydrothermal and dry annealing methods that use low energies. And we are also using electrochemical methods for releasation. And for the anode active material regeneration, we have a hybrid process that includes washing and thermal treatment. And for both of these processes, we are optimizing them regarding energy efficiency, cost efficiency, scalability. And a nice example is shown here from our partner Vito for the cathode active material regeneration based on different pre-treatment options, either via ultrasonication or via liquid-based debindering and materials disaggregation. And you can see on the right hand that we have achieved a very good healing of the LFP active materials with these process steps. The black XRD pattern shows the initial material from end-of-life batteries, and in addition to the LFP, you can see the peaks for the iron phosphate impurities. And in red and blue, you can see the XRD patterns of our regenerated materials. And they only have the peaks for the pure LFP, which demonstrates a successful process. And an even further improved process has already been filed for patent. And as a next step, building on our innovative reuse project, we are further upscaling the process, and our company Cellcircle has already initiated respective steps with the goal to achieve an industrial pilot production already in 2027 with a capacity of approximately 500 tons per year, followed by further process rollout all over Europe to make a strong impact to a sustainable European battery value chain. And now I look forward to a fruitful discussion. Many thanks.
Thank you very much, Andreas. So, well, let's go to the roundtable discussion. I don't know if someone would like to start making some questions or exploring different collaboration pathways. Okay. Yes, Andreas, please.
Yeah, I can start. So first of all, many thanks to our fellow projects, BATT4EU, BATTERY, very nice presentations, interesting activities. So I already see a lot of synergies. No? For example, one could transfer this nice digital twin approach from BATT4EU to our direct battery recycling process in reuse. And also we could use our innovative battery cell sorting process for the demo plant 1 of BATT4EU. So I'm happy to discuss joint opportunities in the future, and look forward to follow-up activities.
Yeah, absolutely. Absolutely.
So I think that David is also really interested in this kind of collaboration because, well, I have talked with him before, but unfortunately he needs to leave. But for sure, I think that this is really interesting. I have a question. Maybe it's because of my misunderstanding concerning the part of the digital twin. So I'm not sure about the similarities of the manufacturing process between different, for example, different chemistries, cell chemistries or cell geometries, even cell process manufacturing processes between different companies. So I don't know how this digital twin is for zero manufacturing could be applied to all these different scenarios. If it is transferable or
so Leonard, what we mean by these digital twins is, of course, specifically developed for certain processes. So the same digital twin of mixing, of course, cannot be transferred to I don't know, maybe calendaring, because the involved physics are completely different. So we are capturing this and we are developing this specifically for a single process. However, the full production model, let's say, if you can manage to interconnect these inputs and outputs of each processes, the battery production systems are built on the same processes, let's say. So, of course, the battery geometry and the chemistry might be different, surely. In BATTWIN, for example, we have two demonstrators. One is LFP prismatic and the second is pouch NMC. So we are trying to use the same models in two different pilots that are building two different batteries by just fine-tuning the process parameters, but by fine-tuning the model parameters, let's say. So the methodology is the same for both cases, but let's say the underlying feeding mechanisms are different.
Okay,
so
thanks.
in that case, it is transferable, but of course at a certain level.
So it should be adapted, but it's really nice. So I don't know if someone has another question. No. If not, maybe I can also continue. So Andreas, I see really fascinating this part of the automation of the okay, maybe Mesfin, you can maybe Mesfin and I are going to talk about the same. For that reason, I give the floor to Mesfin.
Okay, thank you, Leonard. Can you hear me? Yes.
Yes.
Okay. So my question is going to Andrea. So you're mentioning about recycling LFP, and my question is going to be, where do you see this, let's say, the cost of recycling LFP, let's say, compares to that of NMC? Because the people from NMC side, they say that, okay, the cost will be covered by the recycled NMC material. Whereas in LFP, it's more or less a complicated system. And then where do you see, let's say, compares to that NMC, the price that's going to cost?
Yeah, very good question. LFP recycling is really a crucial topic for the standard processes because their value creation is based on the recovery of the raw materials, of the elements, like cobalt, nickel, lithium. And in LFP batteries, we do not have the expensive cobalt, we don't have the expensive nickel, and we have a volatile lithium price and a small content of lithium in the battery cells. So these processes are generally not economic. So we have to pay high gate fees. Nobody wants to recycle them. The direct recycling really enables a possibility to make also this recycling cost efficient and economic, because we are also recovering the value of the functional material to synthesize these, for example, 5 or 10 micrometer thick particles, these lithium metal compounds. It needs a lot of energy, a lot of costs. So this LFP material still has a significant value as a functional material. And if you're able to recover this, then you are able to also perform an economic battery recycling. But also here are challenges. So I think the price of an LFP material are 10 euros per kilogram or lower. So you really have to take care that the processes are really cost efficient. And that's also the focus of our reuse project. And for this reason, we also have included a life cycle costing.
Great, thank you.
So even if FullMap is not in this specific session, I would like to say that I see some potential collaborations here, and also specifically, I'm not the technical people of the project, okay, but specifically for that part of the automatization of the recycling processes. Well, one of the our interest is to include in the design of the new cells and in the simulation and prediction of the platform, this automatization of manufacturing. But I think that we didn't close the loop with this part of automatization of recycling. So I think that it could be interesting to have some conversation in that aspect and how we can work on that direction, or even think about it and because we have specific activities about sustainability, but not for the automatization of that recycling process.
I look forward to it.
Okay. Do you have more questions or comments? Okay. Well, I think that we have finished the whole workshop and the session. So I want to make a closing remarks on this interesting workshop. So just to say that, well, I think that this has been a really interesting exchange between all the different projects and also with the different attendees that are connected online. So I would like to thank all of you for the high level of the technical discussion and the commitment that you have shown for this cross-project collaboration. I'm really would like to thank you. And well, concerning that these discussions on how we can move forward and how we can lead to tangible results, well, we will give some. We will send you an email and propose some ideas on how we can materialize this effort. For example, having different workshops of data collection and ontologies, and also collaborated with the work with the other projects that have previously worked on that aspect, and with the Battery 2030 Plus. Then also we can make some working groups. Well, it depends also on the effort that you would like to put on strengthen this collaboration. But well, I will write to you and I will send you some options, or at least some meetings that we can have in the near future. And well, finally, just to give you a massive thank you for the 11 project teams. Well, at the end, 9 project teams. I don't know, but well, probably the other people will have some problems. And also thanks to the Sustainable Places 2025 conference to host this online event, and to the Battery 2030 Plus initiative that continues inspiring and coordinating this European effort. The last thing that I would like to tell you is that this one is the first one of at least 3 different specific events planning by FULMAP to establish links between projects under the Battery 2030 Plus and more. And well, we are committed to fostering this ecosystem and to follow up how we can do this collaboration. So, well, thank you very much for all the attendees and the speakers. And well, hopefully we will join again in other events.